happy Tuesday. Thank you for coming. I appreciate you being here. I hope you had a restful Easter weekend. Um, just to remind you that the homework 4 and linked list code is due today. I don't know how many. So I'm behind on grading anyway. So we're pushing bank to Thursday, and then I will grade it on Friday. The other thing I have to tell you is that the script assignment, so you should be working with the project. I think, let me pause the recording and check the groups. Where are the instructions for the project? So on the modules page, there's a module called the project. And so if you go to the assignment called project. Yes,
And we're also having the final test.
that's correct. Yeah. These are all the things that I need your project to have. Other questions about project? Okay. So there's an assignment due on Friday for your script. So you should meet with your group and figure out what you want your script to look like. I have uploaded an example. So I did this assignment myself and came up with a situation. Okay, it used to be homework 1, so that's why it says homework 1, but it's the project. So this sort of document, this sort of format, that's what I would like for your script. And so this is without writing code. You don't need to write code for the script assignment. This is just, what do you want your game to look like? What's a sample run of your game look like? And so I have the situation, which is a summary of the cast of Brooklyn Nine-Nine is stealing clickers from the department trainers who come in and give presentations. So you know how presenters like will have clickers to advance slides. The goal for the heist is to steal the clickers. And so I have some comments of this is what I made decisions of, this is how the project kind of looks like. And so that's the goal for this assignment, is to write a script and decide, make decisions of what's the story, what sort of thing is going on. And so this will help you once you go to start writing code. So no code is needed for this assignment, just what's going to be printed. And so the script is, I have some introduction, then I have the user choose the team. You don't need to have them choose the team. Like, it's up to you. This is how I decided to structure it. And so, like, this is, so the way that it works is I have them go through each workshop and say, this is what the workshop's about, and we want to steal it. And so input either yes or no, and then you either succeed or you get caught. So this kind of should help you figure out what is going on in your project. No code required, just figuring out the story. Where do you want to get input? So this document is available to you. Do you have any questions?
What about Lab 6?
What about Lab 6? We're getting to that. Any questions on the script or the project? Yeah.
I saw your script that was kind of like how the game would play out.
Yes.
It doesn't work exactly like that. It's still fun. It's like similar to the exact same thing.
Yeah. Yeah. So like I made assumptions in how my heist works, where I was like, I want them to choose the players and then like where they're gonna choose to steal the clicker or not. That's the decision that I made. You can make different decisions, different creative decisions in how this works. The main idea is I want the situation summary and the script of what it looks like if you were to run the program, and just like copy paste from the terminal over. Other questions about the project or the script? Okay, great. If you've got questions, come talk to me. I'm not available after class today because I'm going to the Giants game,
Oh.
but I am available tomorrow. Okay. I also just want to briefly mention I sent this out in the announcement this morning, where, and this isn't like a judgment on the class at all. It's just something that I've noticed where we tend to split into groups and we tend to work independently, and one person will submit their code, and it's not necessarily collaborative group work. It's more, I've put you in groups and then you do individual work. That's not the goal with group work. I would like it to be conversational and collaborative, which means that you don't have to do all the work yourself. You can work together with your partner or partners and produce something that is the product of all of you. So coming together with all of your knowledge. If you're partnered with someone who knows a lot, then I think you should be, we can have this this thing of pair programming, which is where one person is the driver and then one person is the navigator. So the driver is the one who types and the navigator is the one who's maybe like instructing or like looking over your shoulder or something like that. So if you're in a group where one of you maybe is more knowledgeable, then the person who is more knowledgeable, I would say, should be the navigator, and the person who is less knowledgeable should be the driver. Just because when you're learning code, actually typing it gives you, like, it helps you learn it better. So that's kind of the way that I envision that. And the way that I'd like the paired labs to work going forward. The way that we can do it in this lab, because there's two problems, if you do really want to work independently, you can split it up because there's two problems. So one person can work on one problem, the other can work on the other. So you can do it that way if you prefer to more evenly divide the work, or you can choose to work together from the start through all of that. Anybody have any questions on that? Okay. And like I said in the announcement, this is like, they do this in industry. And so I think it's important to practice it now. Okay. Let's talk about linked lists. So last time we went over, here's what linked lists are. And here's how they work. Here's the main operations. And then we went through linked list code from the lab. What I want to ask is, what are your questions about it? So linked lists are confusing. They are always confusing for everybody. So what questions do you have? Where is this confusion of how does this work? Why are we doing this? Why did we choose to do X instead of Y? Maybe let's talk with your neighbor and share questions first, and then I would like to hear from the neighbor groups. So go for it. Turn to your neighbor and talk. What's your questions? What are points of confusion? Go for it. We're talking with our neighbors of what are your questions about linked lists? Questions or confusions about linked lists?
Oh, yeah.
Sorry, can you say that again? I didn't hear what you said.
I don't understand how
what is. constant.
Yeah, I didn't understand how.
Don't understand how nodes work. Okay.
And just for me, I feel like because it's new,
I don't know what questions to necessarily like
ask.
Okay. I'm gonna give the class 30, 45 more seconds, and then I'll get the other questions, and then we'll go through and answer them. Does that sound good? Yeah. We are about to do lab 6. If you have questions about lab 6, I will take them. I will explain lab 6. I think questions in general. That's good. I'm glad. Yeah, I know some teams have worked really well together. I just wanted to make like the overall comment. Okay, you guys have gone quiet. What are your questions?
I think like for us, like, we're still like learning about it, per se, so like as we learn, we don't really have the question until like we like absorb everything.
Okay.
But one thing for me is that like, I felt like I have like a rudimentary understanding of type insert and delete and node. But I can't like reproduce it on my own. If I was to do it.
Okay. Any other questions from your group?
question. Next to it, and once I looked at the code for lab 6, I was kind of, overwhelmed. I didn't really know what I was looking at, honestly.
Mhm.
But I think taking that one, just like going over it. Probably.
Yeah, okay. Yeah, and so that's kind of why we did the thing on Thursday to go through, here's what this code is doing. Okay, other questions? Or points of confusion? What did your group talk about? Let's go, you guys.
Confused of the, because I'm looking at the lab
Mm-hmm.
right now. And so I'm kind of just trying to wrap my head around the copy over function, how it's like, actually like copy and pasting, and if it's more or less transfer.
Okay. Sounds good. How about the corner? Aaron, Maggie, any questions?
Most of my questions were cleared up. So I wasn't really paying attention since I should have in class, so I was looking at textbooks to like kind of thing. And they
Mhm.
refer to them as elements, so I was kind of confused with elements of the lists. Of the are just its notes.
Yes.
And that's what, yeah. we
Okay.
cleared that stuff.
Okay, cool.
Also a little confused about like how the head works. Maggie, you chop off the head, the entire snake instead.
Yeah.
So like, that's how I.
Yeah, I like that. So yeah, so these are two easy questions I can answer. Oh, that's right. I forgot. Thank you. I will do that momentarily. But we're gonna go through the question first. So yeah, so saying the elements of a list they're the things of the list. And so the way that we represent the things of a list in our code, we call them nodes, same as the elements. Other questions? Roan and John, do you have questions about linked lists?
I think I have a decent understanding.
Okay. Roan, how about you?
Yeah, I think The questions were already answered there.
Okay. Let's see. Jose, anything? All right. You too? All right. I think we got,
I have a question.
yes, what is your
I
question?
think you might have like already talked about it, but why would you like use like a linked list versus like a normal list?
This is a great question. Okay. Any last minute questions? Seeing none, feel free to contribute later. All right, let's go through the top. So the first question is, how do nodes work, especially how to use nodes? So let's go to actually, let me pause this. Okay. So what we do with linked lists is we start with a node. So we have, when we're working with an array, we have spots in the array, right? So we've got like a spot that holds 24, a spot that holds 42, a spot that holds 12, right? We're clear on that? So the way that linked list is different from an array is each spot is its own structure, its own object that lives somewhere in memory. So it's its own object that holds some data and points to the next thing. So the head node, the first thing in our list, contains 24, and it points to the next object in our list that holds 42. So a node corresponds to each slot in the array. So we're still holding all this data. The data still is sequential, which means we go from 24 to 42 to 12 and so on. 24 points to 42, points to 12. So it's still sequential. The order of that data is still there. It's just we represent each spot differently. Okay. And so the way that the node implementation looks like is we've got we have two fields. We've got the data field and the next field. And that corresponds to how we draw it. So if we look at the drawing, we've got we represent it as a box, that's our node. And we've got the data field, that's where the data lives. And the next field, that's a pointer that points to another node in our list. So that's the structure of that. In terms of how we use it, so we can create the node with our constructors. So we've got one constructor, 0 parameters, one constructor that just gives us the data, and another constructor that says, here's the data and where you point to. 3 ways we can make a node. And then we use it with the methods, where getData gives the user the data that's stored in the node. SetData takes in some data and replaces whatever we had before. GetNext says, here's where I'm pointing to. I will give this to the user. SetNext overwrites where we point. So if 24 is pointing to 42 and we wanted to delete 42, we could say, okay, head SetNext to this node containing 12. And we can see how we use it in the LL class, where let's say, so here we can see we're using the .getNext method to move it along. So we get here's where temp points to after this, and then we're saying, okay, now that's equal to temp. So that's how we actually move the temp variable along. There's an instance where we get the data. So like if we use the find method, we can call temp.getData. And so that says, because here we want to see, does that data equal the thing that we're looking for. And so we can use that method in that way. Okay, that was the first question. Did we answer that? Do you have other questions?
Oh. I'm just gonna come up with it.
Okay, sounds good. Anybody else have any other questions about how do nodes work? How do we use them? Yes.
You just like, could you just like give like a brief, like I know that you gave like the whole like detail, but like, could you use like a simplified explanation of like, this is how nodes like work or no?
Okay, so a node is a single piece of data in our list. Single piece of data, and it's an object that stores the data and points somewhere. And so we can access or modify those two things as we need. That answer your question?
Yeah.
Other questions? Okay. Moving on to the second one. Insert delete, knowing is okay, difficult to come up with it on your own. So I think this is kind of typical when you're given this like large piece of code. Before, when we weren't so pressed for time, I had us like write the linked list code in class. But we are pressed for time. And so what I would encourage you to do, if this is what's going on, and this may be good practice for the final exam too, is to, if you start with just like you have a node class and you know that your linked list has maybe the head field and the size field, then come up with the other methods without looking at the code that I've given you. Or look up different linked list implementations and compare and contrast and see, this is how I did it, this is how someone else does it. And if you come up with it on your own, then it forces you to think from scratch. Okay, so what do I want to write about that? So A is you could write it from scratch. B is you could look up other implementations. I would maybe do this first, write it up from scratch first. And then compare yours to others. And then see what you did, what they did, what I did. Overwhelmed on the second look, that's also normal. Linked lists are hard. Remember you went through all of these methods last time, so feel free to open up that document and refer to it for the code review and remind yourself, here's what each method is doing. Okay, let's look at copy over. Okay, so copy over is a method that is called pretty much only in this constructor. So the constructor takes in a node and it says, okay, copy over starting from this node. So let's look at this. So we take in a node and we say, okay, the original temp is that node. And then while original temp is not null, we append its data. And then say original temp equals original temp.get next, which we know is code for move it one space along. Right? When we've got this temp equals temp.get next, we're moving it along one link. So what copy over is doing is we start at the beginning, grab the data, append it to this. This is important for the lab. So do you remember when we talked about the word this, which refers to our object? Like when we were in combo lock, where we said this dot num1 versus just any num1 that we were given, right? It refers to our instance. And so what we're doing here is append is a method that a linked list knows what to do with. And so let's go down to append and see what happens there. So find, insert, delete, remove, append. Okay, so append takes in some data and it says insert at location size. So that says insert at the end. And it set the data to be this data that I'm given. So what it's doing is it's going through, do I have my drawing pad? Yes. So we're going through the node that we're given. So we're given a node, we go through the lists associated with that. So the problem that copy over solves is if we're given just one node, we want to the LL with a node parameter, this is our copy constructor. Remember, a copy constructor takes in another instance of this object and just copies all the relevant information over so that these two objects are copies of each other. And that's what this constructor is doing. And so the way we do that is with the copy over method, which not only says if I'm given a node that I only want the list containing this node. That's not what we want. So if we're given this, node, what we don't want is just the list containing that node. We want everything following that, right? If we want to copy this list, we want all the nodes following. That's what copy over is doing. So we start at the first node and we append it, which would make our list look like that. And then we do temp equals temp.get next. So now we point to the next one and we append that data. Now we've got that node and we repeat until we get to the end of the list. So copy over goes through the nodes that were given and copies all the data over to this list. Yeah.
So it's two lists, one is the data and one is the copied data. Or is the first one just nodes of data and we're copying it into a list?
So this is list number 1 and this list is list number 2, which we are constructing from list number 1. Other questions? Does that answer your question about copy over? So this is our copy constructor that we call it in the code, we call it lowercase n node. That's our variable name. So we're making sure that that data is included in our list. So that's the goal of copy over. So yeah, so I would say copy and pasting, I would say it's more like transferring. Yeah.
You have to just go through with every single node and then.
I mean, that's what this function is doing, right? Because we go, let's go back up to copy over. So we start at the beginning, which is just whatever node we're given. And while we're not null, go away, append the data here and then move along. And so we will repeatedly move along, copy data, move along, copy data until we get to null. And so this will be going through the entire list. Okay. I think we talked about this, just equivalent ways to say it. How does the head work? I like this analogy where if you chop off the head, then the snake is dead, where if you lose the head, then if you, let's say we have this very long paper chain and we've got the first thing, but maybe it's really windy or something. And so if we lose our grasp, then it flies away and we can't grab it back. Then the last one, why use linked lists as opposed to a normal list? This is a great question. Let me think of my answer. So linked lists, as we've described, are, let me find that slide. So they're kind of inefficient, right? We cannot, here it is. So with arrays, we can access by index immediately. That's fast. If we need to find something, we need to iterate through the list. But I think these other items where there's not, for linked lists, they're not fixed in memory. And so we can add new things, no problem. Linked lists also are a little more versatile, where did I say? This is what I want to, this is where I would say that linked lists can provide some advantage, where arrays are by definition linear, right? You have an array that's just like a straight line. You can have multi-dimensional arrays, so like having a 2D array, like a matrix, and that's okay. Or multi-dimensional as you need. But it's still linear, right? We're still working in a straight line or straight lines. For linked lists, the basic implementation that we see here is in a straight line, but it doesn't always have to be. So for a linked list, we can have, actually, I think I want to put it over here. So the basic one that we've seen is just in a straight line. We can have it, the links go backwards if we want to. We can also have it just like do some random things like this. Right? And so this is not linear. And so this is linked lists help us come up with other kinds of data structures that are really useful in computation. And data structures, we can represent them. Some of them we can represent them as an array. You'll learn more about this next class and in 374 as well, and other classes that you take in the department. Where a lot of data structures, we can represent them in array in this linear fashion, but others maybe not so much. Where there's a kind of data structure, which I'm very passionate about, called a graph, which is not your like X, Y, oh, here's the function. The graph is more abstract like this, where we've got nodes and edges, where there's some relationship between these two things, and we represent it with a line between them. And it can hold a lot of complex information. And linked list is one of the ways that we can implement that. And graphs are really important. There's a whole category of algorithms that you'll learn about, graph algorithms that need this underlying data structure because ultimately we need to be able to implement it and run the code on it. And so that's kind of why linked lists may not be especially efficient, but I think they're good at kind of introducing you to these higher level topics. Also, linked lists help us kind of transition from learning about object-oriented programming in general to this is a data structure and we need to define how it works instead of just relying on arrays and saying, oh, we can just append. The question is, how do you append? What does that mean? How do you insert something into this list? We have to actually like look at that function and see how it works and design how that function works and not just relying and assuming that it exists. Okay, that's my tangent. Does that answer our questions? Are there other questions that this brought up for you? Okay. Okay, so say this is a graph. That's not the graph that I'm talking about. Okay, I'm gonna save this document. I will upload this to Canvas later. Okay, now let's look at lab 6. So my plan is we're going to talk about it conceptually as a class to kind of figure out how are we going to do this. And then part of this is going to be in, I'm going to have markers. So I would like you to go up on the whiteboard and try and figure out how it works. And then I think I might split you into groups now and have you move, and then we'll talk about it. So let me pause recording. Okay, we are in our groups. Now we're going to talk through what are we doing for lab 6. So we have gone through the ll.java file and kind of seen here's what these methods are doing. In this assignment, your job is to implement 2 methods. These are kind of more advanced methods and operations than what you've seen previously. So the goal is you're going to implement these methods. The methods do something, then you run the tests and see if it works. If it works, then you're done. So, maybe don't clone it yet. We're going to talk through it. So clone it and make sure you name it correctly. Decide how you want to split up the work. Do you want it to be driver navigator or independent? One person does union, one person does intersection. So the first step is to just look at the other code files, try and see what is the purpose of each, just because there's different files in here. Like there's computer, there's list demo, node, there's random string utils. I will tell you that this is a helper function that where does I forget now that I'm staring at it, I forget where I used that. I think it was in this demo. Now that I'm doing it, I forget why I have that. I think it's something to do with it used to be, oh, here it is. That's why it's here. Random string utils helps us to come up with a random serial number for each computer. So that's more of a helper class. There, I did part of that first problem for you. So just look through the files. Random string utils, I will tell you, is just like a helper thing that gives us some things to do. So these are your two jobs, union and intersect. So let's talk about what that means. So the union of two collections, if we call one of the collections A and the other collection B, we want to produce a collection that includes all the elements in A plus all the elements in B. So any element in common is retained but not duplicated. That's a bunch of words. Let's look at some examples. This is our Venn diagram. So let me actually make a new document so we can draw things. Okay. So if this is our circle, which represents some things of in A, like 1, 2, 3, 4, and then we have another circle B, which also has 5, 6, and 7, and has 3 and 4. It's a Venn diagram. This should look fairly familiar, where A has some things that are unique to that set, so 1 and 2. B has things that are unique to that set, 5, 6, and 7, but they have things in common, 3 and 4. The union of these two sets is just if we colored all of this in. So A union B is 1, 2, 3, 4, 5, 6, 7, which is all of it combined. Are we clear on what union means? Great. Okay, so we've got two examples here. A equals 1, 2, 3, 4, B equals 2, 3, 5, 6. And so the union of those is we just combine it all together. 1, 2, 3, 4, 5, 6. Note that we've got 2 2s, 2 3s. The duplicates, we ignore them. So in the union, there's only 1 2 and there's only 1 3. If we've got this one where we've got 1 and then 5 6 7 8, the union is just 1 5 6 7 8. I've got a note here. So a set is a mathematical structure where, it's a mathematical structure where we ignore any duplicates and the order doesn't matter. However, in this assignment, we're working with lists where duplicates could possibly be allowed and the order does matter. So like it matters in a list if 1 is before 2, but in a set, it doesn't matter if 1 is before 2. So given that, you won't be given any list with duplicates. And the test cases are written so that whatever order you produce it, if it's a valid union, you will pass the test. So those are my caveats, and the answer to those caveats is don't worry about it. Okay, so that's union. I'm going to skip over the hints for a moment. Let's talk about intersection. So if we're looking at A and B, let me take away the highlight here. I've erased the circle. Let's redraw the circle. Okay, so the intersection is just, instead of all of the Venn diagram, the intersection is looking for what's in common. And so what's in common in this Venn diagram is the overlap part of the Venn diagram, where we're just looking at 3 and 4. So we say that A intersect B is just 3 and 4. So let's look at the other examples. If we've got 1, 2, 3, 4 and 2, 3, 5, 6, the things that are in common in both lists are 2 and 3. And here, if A is 1 and B is 5, 6, 7, 8, the things that are in common with both lists is nothing. There's no overlap. So that would be like if A is 1 and B is 5, 6, 7, 8. There's no overlap in these Venn diagrams. They're completely separate. So A union would be all these elements. A union B is 1, 5, 6, 7, 8. But intersect is nothing. So that's also a possibility. Are we clear on what intersect means? Okay, so now is the time where I would like you to, so we've got these two examples. So let's see, my examples are number 1, which is A is 1, 2, 3, and 4, and B is 2, 3, 5, and 6. These are our lists. We're going to assume that these are linked lists. So each of these elements is its own node. Well, so each node stores some piece of data. Each node stores a piece of data. And so we have a list of numbers. And so that translates into a linked list format. We could have written them in array format. And it would look almost exactly alike. We just have it in linked list format where each piece of data is in a box now.
Just the name of the list and then then put in square brackets the index.
Well, no, because linked lists do not allow index. Okay, so let's put a pause on like implementation for now, and we just want to think about this conceptually, which is why I have you positioned near whiteboards. So if we know that A union B is, so union is 1, 2, 3, 4, 5, 6, we know that's the answer. The question is, how do we get there? What's our algorithm to get this answer? And if we know that the intersection is 2 and 3, how do we get there? Okay, so that's example 1. Example 2 is 1 and 5, 6, 7, 8. So let's take these two examples, and I want you to think through, so maybe draw it out like this, draw it as a linked list, and talk through with your partner, how do we find this list? And so one of the things that I require you to do in this lab is to remember how CopyOver uses this? The result, so the way that you store your result is modifying this list. So keep that in mind. So you can assign one of them to be this. And I want you to think through, how do you find out that 1, 2, 3, 4, 5, 6 is the solution? Any clarifying questions that you have? Okay. We have the two pieces. We know the answer. How do we get to the answer? Go for it. Talk about it. Okay, so for union, so some of the ideas I've seen is like we can find the intersection of these two lists, then delete it so there's no duplicates. And then that gives you the union. My concern is, how are we doing this? I agree. So this is the thing about this problem, is that there's a lot of different ways to approach it. And my concern, if you have this conceptual idea of this is how we want to do it, great. And it does theoretically work, amazing. But then you need to be able to translate it into code. And so while I agree that this does work at a conceptual level, I would encourage you to maybe figure out how to find the union on its own. The other idea I saw going around is, what was that? Go through B, and then if so if we go through B, and then if we find that the thing is in A, then delete it again to remove any duplicates. And then so structure this, and then go through the rest of B and add everything to A. So this removes any duplicates, and then this adds everything else to A. That is also an option. Let me tell you the high-level version of what I had, which is where we go through B, and I said if B has something we don't, add it to ours, which I consider A, or this. So if B has something we don't, then add it to our own list. And that's it. So just go through and see, is there anything that we're missing? Then add it. That removes the possibility that we have duplicates, because if we already have it, then we don't add it. Okay. Since we're running low on time, I will tell you my version of intersect, which is very similar. For intersect, I say we go through our list, so A or this. And if we have something B doesn't, delete it from our list. And so that ensures that we will not, so if we have something that B also has, we do not delete it. If we have something that B does not have, then it's not in the intersection and we delete it. Does this make sense? Yes,
So for all these, we're not creating like a third list, we're kind of just like altering one of the already existing lists?
that's correct.
Okay.
Yeah, we modify one of the lists that we are given. And this is, yeah, so it's a twist on the problem. So maybe you think about it as we've got two and we want to create a third. But for this version of the problem, we're modifying one of the lists we were given. Other questions? Okay. Let's look at this. Okay, so I will say that the method find is your friend in this. So maybe review find. And with that, you are good to go. So go ahead and clone the lab and decide among your partners how you want to divvy up the work and go for it. We've got maybe 20 minutes till the end of class, but I will keep this up so you know how to do it conceptually. Now the question is, how do we write this in code? That's normal. That's normal.
That's already 8 minutes.
Okay, it's 5 o'clock, so I just want to bring us back really quickly before I let you go. Next time we will work on this some more. What I would like you to do is share contact information and just like if someone's got the code, zip the project as it is now and send it to your partner. Just so that if next time we'll come back in these groups and if your partner's not there, then they don't start from scratch. If they don't have the code. And if this is still really confusing, please make an appointment, come to office hours, or watch YouTube, Google about this. Linked lists are ubiquitous, and so there's plenty of resources out there, both myself and sources that aren't myself. So use those things at your disposal. And yeah. Okay, so thank you for coming. I will see you on Thursday.